Advanced Algebra 2 students, this is Mr. Hale. These are your 7.8 notes. We're going to be looking at applications of exponentials and logarithmics today. Pretty interesting topic. Some applications we obviously haven't seen yet. So let's jump right into it. I've got a little model for you for exponential growth and decay. You can see these here. For growth, it's f of x equals a times e to the positive kt. For decay, it's ae to the negative kt. The only difference, of course, being that the exponent is negative with the decay. Now, this isn't that different than other exponential growth and decay problems we've dealt with before. We're just using a k to represent a constant, the rate of continuous growth or decay, and then we're using e for the natural base. So again, it's not something that's a huge deal. I'm not asking you to memorize these, but we're going to use them, and if I ask you to use them, I'll give you those models. So here's the first one. And the population of China has increased from about 1.26 billion to about 1.36 billion in the last 17 years. We want to find the value of k. So again, we're talking about using f of x equals, and I'm going to just say y equals a times e to the negative kt. Oops, let me fix that. This is growth, so it's a times e to the kt. There we go. And let's plug in the numbers we know. We know at the end the population was about 1.357 billion. We know it started, that's what the A term is representing, the beginning value, 1.26 billion. And then we have E to the, well, we don't know K, but we know this happened over a 17-year period, so I'm going to put 17K. All right, let's do this algebraically. To solve for k, I'm going to need to first, of course, divide by 1.26. And anytime we have an exponent, we need to undo that with a logarithm. So we're going to do that. So we're going to have the natural log of 1.357 divided by 1.26 is equal to 17k. Now your final step here is just to plug this into your calculator. You're going to do the natural log of 1.357 divided by 1.26 and then divide that number by 17, and you'll get about 0.0044. All right, if you didn't punch that in on your calculator, you better practice that because it's not that easy to do some of these. It's easy to make mistakes. So practice it, make sure you can do it, work with your neighbor or somebody else. If you can't, figure out what you're doing wrong. All right, let's follow that up. So we're going to use that k value to figure out when the population of China is going to reach 1.5 billion. So now I'm going to use that same model, but this time we know k instead of knowing t. So it's kind of the same algebra when you think about it. We know k is 0.0044, and time is the variable we're trying to find. How long will it take? Hey, the algebra is really kind of the same on this. Divide. I'll go work up here. Next step, we're going to take the natural log of both sides. And again, I'm choosing natural log here. I think you guys understand this, but it's natural log because base e tells us that we want to use base e for our logarithm as well. And then the last step here is to do in our calculators the natural log of 1.5 over 1.26, divide by that 0.0044, and see what we get. Now I've got t to be about 39.63. And a quick disclaimer here, if you use 0.0044, you'll get 39.63. If you kept the number in your calculator from step A, you could debate whether, which of those is better. I'm not going to get worried about it too much, but your answer might be about 39.9, I believe. It's still pretty close. It's just slightly different. No big deal. So, because in the end, it's saying when, so this is 39.63 years. So I'm just going to say, remember, this comes after 2000. So I'm going to say late 2039. Okay, we're not going to try to narrow that down to the day. There are too many variables. This model's not accurate enough to try to narrow it down that closely. Not yet. All right, we're going to do a comparison now. India's population, the second largest, or second most populous country, I should say, in the world, was 1.04 billion in 2000, and we've got the model given to us right here. When will India's population exceed China's? Essentially what I'm going to do is this. I'm just going to say 1.04 e to the 0.015 t equals, and we're going to use the model we found for China, 1.26 e to the 0.0044 t. Now I'll tell you, this is a little bit of a tricky one. It is technically possible to solve this using logarithms, like we could do a natural log and then we could break things apart. I debated using that method, but I actually think in one like this, especially since we're approximating values, it might be wise just to use the graphing calculator and just graph it. So I've already punched these numbers in for us. I'm putting India's population in Y1. I'm putting China's in Y2. And then I went to the window. I kind of had to take a bit of an educated guess, and I guessed it would be somewhere between 2000 and 2040, which may or may not be right, but if I can adjust if needed. And then the Y values, I really only need to go up to 1.5, maybe 2. So I thought 0 to 5 would be plenty. And then I can hit graph, and you can see, hey, we've got this. The blue represents India, red represents China on this particular graph. And we've talked about how you can do intersections, and that's what I'm going to do. So I'm going to try to find the intersection here, and there it is. So I've got it to be about 18.10. Just drag that right down there. And so what that tells me then is that it's around 2018. Now these models are a little rough, okay? We're using some estimated populations. There are things that change. China's growth has slowed. Other things have gone on. So these models are a little rough. I will admit that. But the interesting thing is I was just reading today, and even with our fairly rough model, they're saying that sometime around 2022 or sometime between 19 and 22, I guess, is what I was reading. So it's actually, I don't know if it's something to be too proud of, but it's only 1, maybe 2 or 3 years off, pretty close. So it's going to happen fairly soon. All right. All right, let's keep rolling here. All right, the next thing we're going to look at is half-life. Half-life is one of my favorite exponential and logarithmic topics. It's kind of cool. It allows us to do things like dating things that are really old, okay? So kind of cool stuff. Basically what it comes down to is this. If we know how long it takes for half of a substance to decay, we can measure how much is left, and knowing how much it started with, we can determine ages of things. We're going to use the formula you see here, N of t equals N sub O times 1/2 to the t over h. Now we'll put a disclaimer out here. The book has a slightly different formula. Theirs is fine, but I think it's more complex, so I'm going with this one. And if you like the book method better, be my guest, go for it, but get them right. Otherwise, use my method. We'll still get them right, even if you use my method. All right, so N of t represents the amount of substance left. Now that's basically your end amount. N sub O that you see right here is the initial, how much did it start with. T in the exponent represents the time, and H represents the half-life. The way we measure time or half-life will vary depending on the substance. Some are, measured in seconds or even less than that. Others are definitely in years or, very long periods of time. All right, so here we go. We're going to look at plutonium-239 on number 2. It has a half-life of over 24,000 years. How long does it take 12 grams to decay to 1.2? So what we're going to do is use that formula. The end amount for us is going to be 1.2. We're beginning with 12, and we're seeing how many half-lives does it take to get there, or more specifically, how many years. So T over 24,110. All right, so we have a little algebra to do here. The first thing I would do is divide. So 1.2 divided by 12, that's going to give us 0.1 or 1/10. We're kind of mixing fractions and decimals here. That's really okay, I suppose. And then that leaves us with just a lone exponent. And what I'm going to do then is undo that exponent by doing a log base 1/2 of 0.1 is equal to t over 24,110. And hey, you know how to do this, log base 1/2 of 0.1. That's a calculator problem, so go ahead and do that. And then when you get that answer, multiply by 24,110. And when I do that, I'm getting about 80,000 years. If I go to the nearest year, which is a little bit suspect to go that accurate, but we'll go with it. So it's a little over 80,000 years. Again, to go to the nearest year or 10th of year or something like that's probably not the best approach, but it's somewhere around 80,000 years. All right, an unknown substance decays 97% in 100 days. Find the half-life. So this one's a little different. Well, if it decays 97%, well, that means what we're left with is 3%, right? And we started with 100%. That's the percentage, not the days. All right, and then we're going to do 1/2 because that's what our half-life formula says to do. Now here, the time we know is 100 days. What we're looking for is h, the half-life. All right, so I'm going to start by doing this, divide by 100. And we've seen this before. We basically have to get our exponent by itself. We cannot have other stuff hanging out over here. But now we're ready to undo our exponent with a logarithm. So we're going to do log base 1/2 of 3/100ths equals 100 over h. Now to get from here to h might be a little tricky for some of you, but think about this way. Let's multiply everything by h, then divide by the logarithm. So we're going to have 100 over the log base 1/2 of 3/100ths. Okay, and I've got the half-life then to be about 19.77 days. So basically what we're saying is it's about 5 half-lives for 97% of the material to be gone. About 5. And if you sit there and take 100 and divide it by 2 5 times, you get pretty close to that. So it seems like a reasonable number. All right, the last two problems we have I would classify as both things that we've actually seen at some level before, but I think they're worth looking at again. They have their challenges. So after treatment with an antibiotic, a culture of bacteria decays by 7% each minute. How long will it take for 2/3 of the bacteria to be gone? All right, so here's what we want to think about. What we're going to do is we can use the exponential decay from the beginning of these notes if you want, but I'm actually going to keep it a little bit simpler. I'm just going to use our amount equals the initial amount, and let's just say P. It's almost like a banking problem, isn't it? And then it's decay, so I'm going to do 1 minus 0.07 raised to the T. Now, again, I don't really like that I used P there. I'm actually going to change that because, well, how much are we starting with? Well, we're starting with, we don't know. It doesn't say. Well, let's just say it's 100%, okay? The decimal for 100% is just simply 1. So I'm just going to do that. Now, there's one more thing we can do. It says, how long will it take for 2/3 of the bacteria to be gone? Well, that means we're going to have 1/3 left. So I'm just going to simply do this. 1/3 equals 1 minus 0.07. That's 0.93, but you already knew that. Raised to the T power. All of a sudden, this problem just got a whole lot simpler. We can do a log base 0.93 of 1/3, and that's going to be equal to T, and I've got the time to be about 15.14 minutes. You have to use a bit of a judgment call in terms of how far we round, but that seems reasonable. Again, I would argue that you could go back and use the exponential decay formula that we saw on the first slide of these notes. I'm not sure that's really necessary in something like this. To be honest, I'm sure it's not. But if you wanted to use that, you definitely could. We'd find a K value based on the information, and then we'd be able to plug things back in and find our time, basically. All right, last one. Miley's trying to decide which bank to open a savings account. Bank A offers 5% interest, 5% compounding quarterly. Bank B is 4.5%, Nice thing there is that it's compounding continuously. She wants to leave the money in the accounts for 2 years, or the account, I should say. Which bank should she choose? Well, let's solve this as two separate problems, essentially. For bank A, we're going to know the amount of money in the account is. Oh, wait a minute. This problem doesn't tell us how much money she's investing. You know what? It doesn't matter. You can pick a number. What I'm going to do is I'm going to pick $1. Okay. Now, you might want to invest more than that if you start a savings account. That's probably smart. But truthfully, it doesn't matter how much money she invests when we try to figure out this problem. Now, I've already put 0.05 over 4. That 0.05 represents the interest rate. The 4 represents quarterly in value of 4. And it says she's leaving the money in there for 4 years. Now, at this point, this is just a calculator problem. Now, we could argue like, hey, when it's money, you just round 2 decimal places. I'm going to go ahead and go a couple more. And the reason here is since we don't really know how much money she's actually putting in, then it sort of matters. Like if she put $100, she'd have $110.45. And so I think it makes sense to do a couple of extra decimals at least on a problem like this just to see what's going on. All right, so let's keep the information the same in terms of the investment. So this time for bank B, it's $1 again. But this time we're using the continuously compounding interest. So that's P times E to the RT. Now we know R is 0.045, and we know the time is still going to be 2 years. And when I plugged these numbers in, it showed me that she would have close to the same amount, but when you look at it, it's basically right at a penny less over 2 years. Now you could argue like, well, who cares? That's 1 penny over 2 years. You'd have a good point. But with larger amounts of money, that difference would increase to a greater dollar amount. One other interesting thing to point out is I put on there 2 years. Truthfully, it wouldn't matter if this question was 2 years, 5 years, or 100 years. Bank A would actually still be slightly preferable to Bank B, but of course the difference would be fairly minimal unless you're putting in large amounts of money. Hey folks, I hope this works for you today. We'll have some challenges on the assignment, I know, but you're up for it, so work hard, ask lots of questions, and have a lovely day.